Hi everyone, welcome to the PCD of today's Codeforces Round 1021, that was Division 2. And today we'll discuss the first four problems. But before we start, I'll tell you about our all new CP sheet. So, if you don't know, this CP31 sheet is a sheet which contains 31 handpicked problems in all ratings from 800 up to 1900, and the problems are handpicked in such a way as to teach a new concept in every problem. Added to that, every problem has a solution video, and they are still being uploaded. As you can see, 1001s have been uploaded fully, and we are currently doing this rating. And every week, 7 to 8 solutions will be uploaded. Then you also have your discuss section right here, where you can discuss with your friends, and you also have a leaderboard right here where you can compete with your friends about who solves more problems. You can also connect your account directly on this sheet, which fetches your submissions and tells you which problems you have solved. Right? So now that you know about this, you can start practicing, and the link to this sheet is down below. So let's get started. All right. So the first problem of today's contest was this problem number A. We call a phone number beautiful if it is a string of 10 digits where the ith digit from the left is at least 10 minus I. That is, the first digit must be at least 9, second at least 8, with the last digit being at least 0. For example, this number is a beautiful phone number, while this number is not, because on second digit we have 0, which is not at least 8. Vadim has a beautiful phone number. He wants to rearrange its digits in such a way that the result is the smallest possible beautiful phone number. Help Vadim solve this problem. Please note that the phone number are compared as integers. Okay, so what we have been given is that we need to figure out, like we have been given a beautiful phone number. A beautiful phone number, like what is a beautiful phone number defined by? Basically, it is a string of 10 characters or a string of 10 digits S, such that S of I is at least 10 minus I in one indexing, like where this I goes from 1 to 10, right? So here at least 9 would be there, so that means that 9 would be there in a beautiful string. Then here at least 8 would be there, so 8 or 9. Then here at least 7 would be there, and so on, right? So in the input they have given us a beautiful string, and we have to rearrange it so as to make remain it beautiful, like so that it remains beautiful, but we have to minimize its value. We have to make it value as the minimum possible, right? So let's try to do it with via this test case. Like, just take this test case: 9988776655. So that is a beautiful string, as we knew. So the string is 9988776655, right? And as you can see, it is a beautiful string because this first index is at least 9, second one is at least 8, this third one is at least 7, this is at least 6, and so on. So we can rearrange this any way we want, but it has to be beautiful. So we want to make it minimum. So let's try to do that. Now, as you know that, let's say a number has, like, let's fill this blanks greedily. Like, I'll first the most significant bit first, or the most significant digit first. Like, because as you know that we can simply minimize this digit if we want to minimize the entire number. Because if there is a string with a 5 in here and something, anything right here, and there is a string with 6 right here and anything right here, then doesn't matter what the remaining digits are, definitely the sixth one is bigger than this 5 string, right? So if we want to minimize that string, then obviously we will try to minimize the first digit first. So yeah, and of course in a beautiful string, this first digit has to be at least 9, right? So I'll have to fill 9 here, obviously, right? So I have filled 9 here, so I have 1 9 used, like I have used 1 9, so I will cut that away. Now here it has to be at least 8. Our digit here has to be at least 8. So either 8 or 9. So we have both options available to us. But of course we'll choose 8 because we want to minimize the digits. Minimize the number, right? Then here we need at least 7. So I'll insert 7 right here and I'll erase it from here. Then here we need at least 6. So I'll insert 6 right here. Then here we need at least 5. So I'll erase this 5. And here at least 4 we need. So we need 4, 5, 6, 7, 8, or 9. So we have 6 options for there. But we don't have a 4 in our bag. The lowest we have is a 5. So I'll put that, right? And here we need at least 3. So we'll put a 6 because that is the lowest that we have. And then we can put a 7. Then we can put an 8. Then we can put a 9. Right. So as you can see, this is your final answer. 98765 56789. So I think that is the answer also. Yeah. So essentially what I did was that at every step I need to ensure that my S of I was at least 10 minus I, right? So out of the bag, like I had a bag of numbers, right? I had a bag of 10 digits initially, out of which I could place the digits into my string. So out of the bag that I had, I found the smallest number, which was at least 10 minus I, right? Like at this point I had 1 9, 1 8, and 2 7, 2 6, 2 5s in my bag, and I needed at least 7 to put here. So I put 7 because I had 7 in my bag, and that is the smallest number, at least 7, right? So that's why I put 7 here. So that's what essentially you will do. That just find the smallest number, which is at least 10 minus I. So essentially, what you can do is just maintain a multi-set, a multi-set of characters maybe, like in C++, just maintain a multi-set of char, and initially just insert all of the, just insert all of the um, letters that have been given to you in the input string, and one by one, like at the ith step, just find the lower bound of 10 minus I, m dot lower bound 10 minus I, which will give you the iterator of the first element, which is at least 10 minus I. The first element, which is at least 10 minus I. And since the elements in this multi-set are in sorted order, so we can simply do that, right? And that's your answer. So I think it should be clear that what we are doing, at every step we are greedily trying to put the minimum integer that we can put. So someone might have a doubt in this, that what if we get stuck? Like, what if at some point I don't have any number which is at least 10 minus I? Like, what if I am filling in these numbers, right? So let's say I filled in something here. I have to fill 9 here. Then let's say I filled in 9 here. Then let's say I filled in 7 here. Then let's say I filled in 7 here. And at this point, this is I equals to 5, right? In one indexing, this is 5. So I need at least greater than or equal to 10 minus 5, which is 5. I need at least 5 in this index. But what if out of all the 6 characters that I have, like out of the 6 characters that I have in my multiset, what if all of them are less than 5? So what if I get stuck there? So my claim is that this will never happen. Like if you follow my algorithm of greedily picking the smallest numbers each time, then this case can never appear. This case can never appear. Like if you just greedily pick up the first index, which is at least 10 minus I, at these at all the indexes. Like if you just put all of the numbers one by one, such that at each index the number you put is at least n minus I, then this will never happen. And how do I prove that? See, so what you are saying is that what if we don't have enough numbers which are at least 5? So here we need at least 5, right? Here we need to put at least 5. So but what if we don't have enough numbers which are at least 5, right? That's what you are asking. But let me ask you something, that in the original input we know that it is a beautiful string, right? The input is guaranteed to be a beautiful phone number, that is guaranteed. So we can be sure that it satisfies the constraints of a beautiful string, right? So what does that mean? That in the input, like this is my input, okay, this is my input. So in my input, the first 5 digits, like definitely the first digit will be greater than equal to 9, second digit greater than equal to 8, third digit greater than equal to 7, then greater than equal to 6, and greater than equal to 5. We know that this will be the case, that uh, this element will be at least 9, this will be at least 8, and so on. So I can say that all of the elements, like all of these 5 elements, will be at least 5. These will be at least 5. Greater than equal to 5 elements, there are at least 5. So my claim is there are at least 5 digits greater than equal to 5, right? Because in the first 5 boxes only greater than equal to 5 digits can appear, and so I have at least 5 numbers. Like in the first 5 we have all the numbers which are at least 5. Maybe in the later half also we do have some numbers. That's why I'm saying at least numbers, at least 5 numbers. So there are at least 5 digits which are at least 5. There are at least 5 digits whose value is greater than equal to 5. And when we are making a string, when we are making a string, we were concerned that what if when I reach here at the fifth index, I run out of the digits which are at least 5. Like I do not have any digit in my multiset which is at least 5. But that's not my concern, because I only used 4 digits up till here. Like I have only placed 4 digits up till here. Any 4 digits. Like I don't care what they are. I have only used 4 digits. And I know that I had at least 5 digits greater than equal to 5. So therefore, at least one digit is remaining, which is greater than equal to 5. Therefore, we don't need to worry about running out of digits at each index, because we'll never run out of index, because the initial input string also is beautiful. Alright, so that is the proof of why the algorithm is correct, right? So that's the solution, and I'll show the code now. Yeah, so int t c in t while t minus minus string s c in s multiset of character m. So this is my input. So for auto x in s, I'll insert m into x, right? Now for int I equal to 9, I greater than equal to 0, I minus minus. So what I am doing is just iterating from 9 to 0. Like basically, because I want the first one to be at least 9, then at least 8, then at least 7. So what I'm doing is I'm printing lower bound of I. So in my answer, I am pushing back m dot lower bound I, or essentially I'm not storing my answer. I'm directly printing it to the terminal. So cout star m dot lower bound I plus 0, and m dot erase m dot lower bound I plus 0. So why plus 0? Because in this multiset I have stored the characters. I have not stored the actual numbers from 0 to 9. I have stored the characters. So I need to give it a character. Like I am giving the character 0, or basically the character for I, like the ASCII value of 48 plus I, so that it behaves correctly. And then then I outputting the character, right? So anyways, that is the logic here. And finally also I am printing a new line, of course. So yeah, that is the code. And okay, I hope you understood. If you didn't understand, then you can leave a comment on the YouTube video. All right, so let's move on to the problem B. Sasha and the apartment purchase. Sasha wants to buy an apartment on a street where the houses are numbered from 1 to 10 to the power 9 from left to right. There are n bars on the street located in the houses with numbers A1, A2 up to AN. Note that there might be multiple bars in the same house, and in this case, these bars are considered distinct. Sasha is afraid that by the time he buys the apartment, some bars may close, but no more than k bars can close. For any house with number x, define fx as the sum of absolute value of x minus y, mod of x minus y, over all the open bars y. That is, after closing some bars. Sasha can potentially buy an apartment in a house with number x if and only if it is possible to close at most k bars, so that after that fx becomes minimal among all the houses. Determine how many different houses Sasha can potentially buy an apartment in. Okay, so what we are doing here is, like, the problem statement says that Sasha wants to buy a house. Sasha wants to buy a house, right? But he is a drink, like, he is an alcoholic, a very bad one, in fact. So he wants to make sure that, like, there are 10 to the power 9 houses, right? There are 10 to the power 9 houses numbered from 1, 2, 3 up to 10 to the power 9, and they are arranged in a line, like they are on a straight road. Like, the first house is at coordinate 1, then second house at coordinate 2, and so on, right? So there are 10 to the power 9 houses. So Sasha has 10 to the power 9 options to buy a house in. Now Sasha wants to buy that house, that house such that the total distance to all the bars is minimum. Like, for example, let's say that there is a bar in the building 1, and there is a bar in the building 4, and there's a bar in the building 6, right? So Sasha will buy a house at a position x. Like, Sasha will buy a house at a position x if and only if the total distance, that is x minus 1 mod plus mod of x minus 4 plus mod of x minus 6, like, this is a total distance from his house to all the other bars, total distance. So this should be minimized. Like, he will buy that house for which this distance is the minimum, right? So let's calculate this distance for some values. So let's say this is fx, right? They have called this f of x. So let's calculate this f of x for different values. So let's call let's calculate f of 1. F of 1 mein it will be 3 plus 5, which is 8. Then f of 2 will be what? F of 2 will be 1 plus 2 plus 4, which is equal to 7, right? Then f of 3 will be equal to 2 plus 1 plus 3, which is equal to 6. F of 4 will be equal to 3 plus 2, right, which is 5. Then f of 5 will be equal to 6. F of 6 will be equal to 7, right? So I have calculated these values. Like, as you can see that these values are there, and of course like, you can go till 10 to the power 9. Like, he has 10 to the power 9 options for this x value. Like, where does he want to buy his house in, right? But out of all the options, like, let's say if I go even beyond this 6, like if I calculate f of 7, then f of 7 is what? 1 plus 3 plus 6, which is 10. So as you can see that if I keep increasing my x after 7, my f will keep increasing. Like, the distance is increasing from all three of these points, so therefore the distance will obviously increase if I go more to the right, right? So I am only concerned about these values. So out of these, as you can see, the minimum is at 4. Like, minimum value of f is at 4. right? So therefore, Sasha can only buy the house 4. Like, since f of 4 is equal to the minimum value of fx over all x. Since f of 4 is the minimum value of fx over all x, Sasha can buy house 4. Sasha can buy I mean house 4. He can do that because fx is the minimum for x is equal to 4. The minimum value for f of x is coming out to be at the index 4. F of 4 is 5 and other f are greater than that. Right. Now let's take one more example. Let's say that I have bars at the places 1, 3, 5 and 7. Right. So now also let's try to calculate this. Now I'll make a table for better understanding. So let's say I have x and I have fx. Okay. So let's calculate this values for 1, 2, 3, 4, 5, 6 and 7. Okay. So I'll calculate this, and this is 2 plus 4 plus 6, which is 12. Now at 2 it is 1 plus 1 plus 3 plus 5, which is 10. Then at 3 we have 2 plus 2 plus 4, which is equal to 8. Then at 4 also we have 8. Then at 5 also we have 8. Like, you can verify this easily. Then at 6 we have 5 plus 3 plus 1 plus 1. So we have again 10. And then at 7 we have 12. Right. So as you can see that the value will be increasing after this. So we won't look at them. But as you can see, the minimum value is 8. The minimum value of fx is 8. And it is actually occurring at 3 different positions. Like at 3 also it is occurring, at 4 also it is occurring, and at 5 also it is occurring. So actually, Sasha can buy 3, 4 and 5. Sasha can buy the houses 3, 4 and 5. Right. That is the thing here. That according to the problem, Sasha can only buy those houses for which Sasha can buy the houses x, for which fx is the minimum value of f. Fx is the minimum, right? But actually, they have given us one more liberty. Okay, they have given us one more liberty, that we before choosing an apartment. Okay, before choosing an apartment, we can delete at most k bars. We can delete we can delete at most k bars from the list. Like for example, here we have 1, 3, 5 and 7, right? We have 1, 3, 5 and 7. So or let's say I take one more test case, a better one. Let's say we have, let's just take the third test case. Okay, like I have 6, 7 and 9. I have three apartments, 6, 7 and 9. I mean, sorry, I have three bars. First in the house 6, second in the house 7, and third in the house 9. So I have three bars, and my k is equal to 1 for this test case. My k is equal to 1 for this test case. So what I can do is I can delete at max 1 bar from this list, and then do the process normally. Like the process of calculating this fx. Like when I calculate this fx, and if it is the minimum, then I can buy that x. So this process I will do after the deletion, right? So okay, I can also not delete anything. Like I'm not forced to delete anything. So let's try that what will happen if I don't delete anything. Okay, so let's say if I don't delete anything, so the bars are 6, 7 and 9. So let's calculate again the values of fx. So x and f of x, let's say 6, 7, 8 and 9. So for 6, for 7, for 8 and for 9. So for 6 it will be well, the value will be what, 1 plus 3, which is 4. For 7 it will be 2 plus, sorry, 1 plus 2, which is 3. Then it, for 8 it will be 2 plus 1, which is, sorry, which is 4, and for 9 it will be basically 2 plus 3, which is 5, right? So this is my table. So as you can see that at 7 it is coming to be minimum, right? So we can actually buy house 7. We can buy house 7 by default, right? Okay. But actually, and of course in this case we cannot buy any more houses, like without deletion we cannot buy any more houses. Okay. But we can actually delete one house, like that is our uh, liberty, that actually we can delete one house to buy. We can actually delete one bar. We can delete one bar to try and buy some other house. Like we are able to buy the seventh house without deleting anything, but we can also try to delete some things and buy some other houses, right? Like for example, let's say I want to buy sixth house. Okay, so can I buy sixth house? Can I do that? So let's figure that out. Like let's try to buy sixth house. So my claim is that if you delete this 9, if you delete this 9, then you will be able to buy this sixth house. So let's prove my claim. Like let's look at what happens if I delete a 9. So let's say I delete a 9. So what will happen? Only have the 6 and 7 as my bars. So if I calculate the f value, this is my x, this is my fx. So let's calculate it for 5, 6, 7 and 8. So for 5 it has come to be 3. For 6 it has come to be 1. For 7 it has come to be 1. And for 8 it has come to be 3. And for 9 it has come to be 5, and so on. So as you can see that the minimum is 1. The minimum is 1 and it is occurring on 6 and 7. So Sasha can buy 6 or 7, right? So if he decides to delete the bar number 9, like if he decides to delete this, then he can actually buy 6 or 7, right? And if he doesn't choose to delete anything, he can buy this house number 7. Now actually he can also buy houses number 8 and 9 also. Like currently we know how to buy 6 and 7. Like to buy 6 he can delete 9 from this list, and to buy 7 he can simply do nothing. Like he can simply buy 7 by doing nothing. But my claim is that we can also buy 8 and 9. Houses 8 and 9 are also buyable. And so how would we buy those? So to buy 8 and 9, what you can simply do is delete this 6. Like instead of 9, just delete this 6. Okay. So what will happen? Your bar, the remaining ones will be 7, 9, right? So 7, 9. Now we try to again calculate these values for x and for fx. So let's say we do it for 6, 7, 8, 9 and 10. Okay. So for 6 we have 1 plus 3, which is 4. For 7 we have 2. For 8 we have 2. For 9 we have 2. For 10 we have 4. Right. So for these three values, the value of f is minimum. So Sasha can actually buy 7, 8 or 9 if he deletes the sixth one. Like out of the three bars, if he deletes the sixth bar or the bar at the house 6, then he can simply buy 7, 8 or 9, right? So in one case we are able to buy 8, 9, 8 and 9. Like if we delete a 9, wait, sorry. In one case we can buy a 7 if we don't delete anything. Then in another case, if we delete a 9, then we can actually buy a 6 or 7. And if we delete a 6, if we delete the 6, then we can actually buy this 7, 8 or 9, 7, 8 or 9, right? And in fact, if we delete this 7 and instead of this 6, like if I delete this 7, then you can verify by yourself that we'll be able to buy the houses 6, 7, 8 and 9. The four houses we can buy. So basically, you can just select, like you can just take the union of all of these sets. Like just take the union of 8, 9, like, sorry, of this 7, then 6, 6, 7, or 7 8 9 or like 6 7 8 9. So the union of them is 6 7 8 and 9. Like out of all the possibilities, in all the different possibilities, all the houses you can buy are these ones. Like you can buy these ones by deleting different k bars. Like at most k bars you can delete. So by deleting different bars, you can eventually buy these four houses, and you cannot buy any other house if you can only delete k bars or one bar basically. So therefore your answer is 4 in this case. Your answer is 4. Okay, your answer is 4. So this is what the statement means, that you are allowed to delete some k bars, and like you are not actually deleting them. In fact, like my point is that if to buy different houses, if you want to delete different sets of k, like if you want to delete different bars, then also it is allowed. Like for example, um if your bars are something like what, 1 2 3 4 5. Okay, so to buy this 2, right? If you want to buy this 2, then I'm claiming that you will have to delete at least 5, like either 5 or 4 or 3. Like if you delete at least one of them, then you will be able to buy 2. You can verify this by yourself. And if you want to buy 4, if you want to buy 4, then you'll have to delete either 1 or 2 or 3, right? So my point is that you can buy both 2 and 4. You can buy 3 also if let's say k equal to 1. So you can buy 2 by deleting either 3 4 or 5, and you can buy 4 by deleting either 1 2 or 3, right? But you cannot actually buy 1 and 5. Like I am just telling you that. Of course you don't know why that is. I'll explain that. Okay, so we have 2 4 and 3 as the answer. So the answer to this test case will be 3. And this is 3 because you are basically allowed to delete different bars. Like my point is that you are allowed to do an operation on k. Like my point is, just listen here, hear me out, that if it is possible to buy the house x using some deletions, using some deletion, then count it, then count that x. Okay, so what I am saying is that it doesn't matter if to buy different houses, you want to you will have to delete different what, like if you have to delete different bars, different sets of k bars, then it doesn't matter. Like that is no problem. What I'm saying is that even if to buy different houses, like for example, to buy this 2, you had to delete this 1, and to buy this 4, sorry, to buy this 2, you had to delete this 5, and to buy this 4, you had to delete this 1. So you can do that, it doesn't matter. Like you will count both 2 and 4 in your answer, which means that you are not actually deleting the bars. You are not actually deleting the bars. You are saying that if I had deleted these bars, like if I had deleted this 1, then I can buy 4. If I had deleted this 5, then I can buy 2. That's what I'm saying. So that is what you have to tell them, that how many houses can you possibly buy, like how many different houses are possible to buy, like not concurrently. You don't have to buy all of them. You just have to tell them about the possibility. Right. That is the problem. That is the question here. So at this point, till this point, I was only explaining the problem and the samples. Like till this point, I have only explained the problem and the sample test case. So if you know already about that, then I think you can. I think you could skip till this timestamp. So I think I'll just comment on the YouTube video that you can skip till here. So now that we have read the problem and understood the problem correctly, that what actually we have to do, now we can actually go ahead and solve it. Okay. So how do we solve this? Now consider, okay, a case like initially our bars were located at positions A1, A2 up to AN, right? Like our bars were at these n houses, right, initially, and then we deleted some of them. So now let's say the final array after deletion is b1, b2, b3 up to bm, right, where m is less than equal to n and m is greater than equal to n minus k, because we can delete at most k numbers, right? So it should be at least n minus k. So basically I have deleted um, some bars from this list of bars, and I have gotten this new list. So how do we determine that using these how, using this new list, how do we determine that which house can I buy? Like if I delete those houses and like if I get this new list, then which houses can I buy in this list? Like not in this list, but according to this list, if I just calculate my x and fx, like if I calculate my table of x and f of x according to this list, then which houses will have the minimum distance or the minimum total distance? Okay. So how do we determine that? That which houses can we buy? So let's think about that. So if we have my b1, b2 up to bm, this is my new array. After deleting um, those numbers from this array, like at most k numbers from this array, I have this new array, right? So what is fx? Like the value of fx, what they have defined? They have defined the value of fx as absolute value of x minus b1 plus absolute value of x minus b2 and so on up to absolute value of x minus bm, right? This is what our fx is, and we want to minimize this. Like we want to choose an x such that the value of this function is minimized. Okay, we have to choose an x such that the value of this function is minimized. So what do we do? Like how do we minimize this? Now actually the thing is that it is a fact that if this number, like if you choose x as a median, like if x is a median of this set, like of b1, b2, b3 up to bn, b1, b2, b3 up to bm, if x is a median of this set, then you can be sure that fx is minimized. Then fx is the minimum possible. Like that's why my claim is that if you choose x as the median of this set, if you choose x as the median, then fx is the minimum possible value. Like that is a very well known fact there. Like in fact I remember that in one of my earlier PhDs also I have explained this fact, and I've also proved this fact. So if you are interested in the proof of this fact, then you can actually go to this site. Like you can just search minimum absolute deviation, and you can look at this sorry, what have I opened? Okay, so you can go to this website and read this article, which proves that uh, this minimizes. Yeah, you can look at this actually. This is the nice article which you can look at to get the proof that why do you choose the minimum? Oh, sorry, the median. Why does the median minimize this fx? Why does this median minimize this fx, which is the absolute deviation का sum? Okay, so um, yeah. So anyways, basically my claim is that after deletion, if your array is b1, b2, b3 up to bm, then you have to select the, like you can buy a house x if x is a median. Basically, once you have deleted these numbers um, from this list and gotten this list, then you can buy all those houses x for which x is a median. Now, what do I mean by median? Like, let me just define what a median is. Okay, so if you have odd number of elements, like let's say your elements are 1, 2, 5, 6, 8. Okay, then your median is 5. Okay, your median is 5. Why? Because that is the definition. Like in case of odd number of elements, your median is the middle element. Okay, this is your median. And in case of even elements, in case of even elements, let's say we have 1, 7, 1, 7, 10, 30. Okay, you have this four elements. So you have two medians right here. Like you have two medians, and also every value in the middle also, like 7 7 is here, 10 is here, so in the middle also there is 8 and 9. So this 8 and 9 are also a median. So basically I am saying that this array contains four medians. Okay, this array has four medians: 7, 8, 9 and 10, whereas this array has only one median, which is 5. So basically, if after deletion your bars are these, if your bars are these, then you can only buy the house 5. And if after deletion your bars are these, then you can buy any house from 7, 8, 9 or 10. And I can even verify this, like what I told you above. I can even verify using that. Like for example, when I showed you that, let's say um, you have 1, 4 and 6. 1, 4 and 6, then this has only one median this has, so you can only buy the house number 4. So as you can see, the house number 4 is the minimum. So therefore, Sasha can buy only house number 4. Then let's say we have 1, 3, 5 and 7. So there are two medians right here. There are two medians. So therefore, Sasha can buy the houses 3, 4 and 5. So as that's what we got as an answer when we calculated the values. So Sasha can buy 3, 4 and 5. And let's say we had 6, 7, 9, right? We had 6, 7, 9. So if we did not delete anything, in that case Sasha can buy only 7. So in that case Sasha can buy only 7. Then if we delete 7, or sorry, let's if we delete 9, if we delete 9, then Sasha can buy either 6 or 7. Like this array is of length 2, and for length 2 array, these two are the medians. So there are two medians in this array, this 6 and this 7. So Sasha can buy either 6 or 7. And let's say if we delete 6, so the array is 7 and 9. So the array has three medians: 7, 8 and 9. Like these two are the middle elements, and any number between these elements also will minimize your effects. So even 8 will also minimize. So 7, 8 and 9, this also Sasha can buy. So as you can see that my logic works perfectly. Okay, that the median, like if x is a median of b1, b2, b3 up to bm, then fx is the minimum possible. Therefore x can be bought, the house x can be bought. Okay, so 1, 2, 5, 6, 8, may we can buy the house 5, and in this array we can buy the houses 7 to 10. Okay, so it works perfectly. But now actually, how do we determine? Okay, so now the problem boils down to, like, you have to count the number of values of x, count the number of values of x for which um, it is possible to delete at most k elements. Okay, at most k elements from the array such that x is the minimum. X is the median. X is one of the medians. X is one of the medians. One of the medians of the remaining array. Right. Count the number of values of x for which it is possible to delete at most k elements from the array such that x is one of the medians of the remaining array. Right. That is what we want to calculate. The problem boils down to this, because that's what I have told you, that if x is a median, then we can buy that house. So we can delete at most k houses. So calculate the number of x such that we can buy that house, and we can buy it if it is possible to delete k elements such that x is the median of the remaining elements. Okay, so this is what it boiled down to. So let's try to solve this problem now. Okay, so now how to solve this problem? Now actually you can visualize it using a diagram. Like, let's just draw it on a number line. Just draw the points on a number line. Like for example, if I want to let's take the last test case. I have 6 points: 1, 2, 5, 9, 10, 13. Right. uh, I have 1, 2, 5, 9, 10, and 13. Okay, so let's say I want to like, there's an x here. Like, just assume that there's a point here and I want to buy this house. Like, I desperately want to buy this house. So I am asking you that is it possible to buy it? So like, it is between 2 and 5, so it means it is either 3 or 4, right? So either 3 or 4 I want to buy. So can I buy it? Can 3 or 4 become the median? That is the question now. And we can delete at most two elements, right? So if I want that x is the median, now actually one more definition for the median can be that, like, a certain value x. Like, if x is not equal to any data point, like if x is not equal to any of these red points, then x is a median if and only if the number of values to the right of it, like the number of values to the right of it, are equal to the number of values to the left of it. Like, there are, in the left there are two values and in the right there are four values, so therefore x is not a median right now, right? So that is the median. Like, if there are equal number of values to the right and to the left, then we can say that my x is a median, right? Given that it is not a data point, like it does not coincide with a data point. Okay, so how to deal with that, I'll tell you later. But let's say that right now we are dealing with those points which are not, which are not a data point. So any x which is not a data point, it is a median if and only if the number of points to its right are equal to the number of points to its left. Okay, so currently the number of points to its right are 4 and to the left are 2, so it is not a median. But we can actually delete at most two elements and try to make it median. So what we can do is just delete any two elements to its right which are, like, to its right. So just delete any two elements to its right. So let's say I delete this and this from the array. So my new array becomes what? 1, 2, 9, and 13. So 2 and 9 is the median. So therefore, one of my medians is also x. Like, let's say x is equal to 3. So if x was 3, then it is between 2 and 9, and therefore I can buy it. So basically, my buying x is possible. Like, buying x is possible because I can delete two elements from this right one and make them equal. So in general case, let's just assume that um, we have some points, some data points we have, like b1, b2, b3, and up to bm we have. right? So let's say you are between something, like let's say you are here. Let's say you want to buy this house. Okay, you want to buy this house which is X. So before X, if there are P data points, and after X there are Q points or Q bars, then we want that P should be equal to Q, right? But if it is not equal, then we'll delete some points from the greater one, like whichever one is greater among P and Q, we will delete some points to make it equal to P, or to make it equal to the other one. So how many will we have to delete? So obviously we'll have to delete the difference of P and Q, like absolute value of P minus Q. We'll have to delete these many houses, or sorry, these many bars, right? And we can only do that if that is less than equal to K. We can do that if it's less than equal to K. So we can delete those bars right there, like whichever one are greater. If the difference is less than equal to K, then we can simply delete them, right? So that is the case when X is not a data point. But what about the case when X is a data point? Like let's say we had, um, let's just take the same test case. We have 1 2 5 9 10 13. 1 2 5 9 10 13, right? So what I am saying is that, what if we want to buy this 2, for example? Like let's say I want to buy this house at 2. Okay, let's mark it green. So I want to buy this house at 2. So can I buy it? Okay, now in order to buy it, what do I need to ensure? That 2 is one of the medians. 2 is one of the medians. So let's say that to the left of it there are there are 1 points, and to the right of it there are basically 4 points, right? So at the first glance, you would say that, okay, since k is equal to 2, since k is 2, and we cannot delete, like let's say if we delete 2 points, if we delete 2 points, then also to the right of it 2 will remain. Like to the right of it 2 will remain, and to the left of it 1 will remain. So therefore x is not a median, and therefore we cannot make sure to take 2. Like at the first glance you might say that, right? That since the difference, like initially to the right was 4, to the right it was 4, and to the left it was 1. So since the difference between 4 and 1 is 3, which is greater than k, so it is too large, so we cannot actually take 2 as an answer. But the thing is that if it is a data point, then some things change. Like what changes? Basically, since let's just try and deleting this. So let's try to delete this and this. Okay, so what does the array become? The array becomes 1 2 5 and 9, right? So as you can see that even though to the right of this two there are two elements, and left of this two there are one element, but since these two are the medians, like then also it is the median. So even though there is one element to the right of it, I mean, even though there is two elements to the right and one element to the left, it is a median. So basically for our data points, the condition is that it can have one difference that is tolerable. Like let's say I have 10 right here, which is my data point. Like 10 is one of the bars. Okay, 10 is the one of the bars, and before 10 I have, like let's say I have four numbers in my sorted array, and after 10 I have five numbers, 1 2 3 4 5, and this is a sorted array, right? Okay, so in the sorted form, out of 10 elements, the 10 is the fifth element, right? So actually 10 is one of the medians in this case. Like this 10 and this number are the medians in this case. So even though there is an extra element to the right, we don't mind, because in that case also 10 is extra element. And let's say that these are 10 elements, and let's say that to the left of 10 there are 5 elements, and right of 10 there are 4 elements. So that is also tolerable. because this and this are the medians in this case. So the thing is that if x is a data point, then I need that finally, like let's say I have p, like if let's say my data point is like there are some data points and I have this data point right here, and like I have um, p data points to the right of it and q data points to the left of it. Okay, then this can be a median if the difference between p and q, like either p equal to q or p minus q difference is equal to 1, like so basically less than equal to 1 I can say, right? But initially if it is more than that, like let's say here we have like let's say to the left of it we have two numbers and to the right of it we have, let's say, seven numbers, right? So ideally what we would do is 7 minus 2, which is 5, so k should be at least 5. That's what we would say. But actually we don't need to make them equal now. We can make them one less, like 7 can actually just bring down to be 3. So 2 and 3 will support it, like 2 and 3 is no problem. So our final condition would be that absolute value of p minus q minus 1. Like what we would do is that initially the p is 2 and q is equal to 7. So we would take the absolute value of p minus q and say that 5 is the answer, p minus q, and say that 5. But actually what we can just do is we can also subtract minus 1 here, and that should be less than equal to k, because we don't need to make them equal. We can perform one less operation. We can, like, these p minus q operations will be there if we want to make them equal, but since we don't want them to be equal, we can perform one operation less. Okay, like if we were deleting 4 to make them equal, we can just delete 3 of them to ensure that the difference is 1. So that's why I'm doing minus 1 here, and that is the number of deletions. So the number of deletions should be less than equal to k, right? It should be less than equal to k. So what I can say is that the difference of p minus q should be equal less than equal to k plus 1. This is the condition for which my AI can become median. Like what I am saying is, okay, now let's go to the problem. Like let's say initially our array has been given to us that one data point is a0. Let's say I have sorted it. Like I have sorted it. So the first is a0, then second is a1, third is a2, and so on up till we have a of n or a of n minus 1. So I can actually, so my a of I can be a median. My a of I can be a median if to the left of it, let's say there are p. Like okay, let's count that how many are left of it. So to the left of it there are I actually. To, like, for a of I there are I elements to the left of it. Like from a0 up to a of I minus 1 there are I elements. So to the left of ai there are I elements, and to the right of a of I there are n minus 1 minus I elements. So basically my p is equal to I and q is equal to n minus 1 minus I. And what I want is absolute value of p minus q should be less than equal to k plus 1, right? So if I put these values into here, so I want that absolute value of I minus n minus 1 minus I should be less than or equal to k plus 1, right? So from here you will get a range of values of I. You will get a range of values of I, and those are possible medians in your data points. Okay, so let's say that okay, let's say you have 6 numbers or something, or let's say you have eight data points, like a0, a1, a2, or let's just take 6 for now, a3, a4, and a5, right? And your k is equal to 6, oh sorry, k equal to 2, let's say. Okay, so so let's try. Now let's just iterate over um, our data points here and just check that which data points can be our median. So let's say, can a not be median? Can a not be a median? Let's check that. It can be a median if this satisfies. Like I minus n minus 1 minus I should be less than equal to k plus 1. So 0 minus uh, 6 minus 1 minus 0 should be less than equal to 3. So is this it? Like, is this the case? No, because 5 is not less than equal to 3. So we cannot make a naught as the median. It is not possible to make a naught as the median. Okay, right. So now let's check a1. Let's check a1. So for a1, can we make a1 as the median? Let's try. Like we'll put 1 here. So 1 minus 6 minus 1 minus 1. So what is it? This is basically equal to 3. So which is less than equal to k plus 1, which is 3. So therefore we can take a1, right? And then you can verify that we can take a2, we can take a3, we can take a4, and we cannot take a5. Okay. So these are the 4 data points that we can take. But what about in the between ones? Like, what about in between ones? The thing is that you can actually buy every house between a1 and a4. Like any houses right here, or right here, or right here, you can buy all of them. Okay, and you cannot buy any other house outside of these a1, like outside of these houses, like before a1 or after a4, you cannot buy. Okay, so that's why basically your answer would be just a4 minus a1 plus 1. That is the number of houses from a1 to a4, because at every point there is a house. So that's your answer, a4 minus a1 plus 1. Okay, so this is my answer. And yeah, so like if I illustrate on this example, 1 3 5 9 10 13. Okay, I have 1, I have 3, I have 5, 9, 10 and 13. So, and yeah, k is equal to 2 here, right? So as we saw above, k was 2, n was 6. So for k2 and n6, we were able to delete a1, a2, a3 and a4. So in this case, sorry, not delete, we were able to purchase a1, a2, a3 and a4. Sorry, not 1 3, 1 2. The input is 1 2 5 and 9 and 10. So we can purchase houses 2 5 9 and 10. It is possible to purchase them. So the answer is that all of the houses between 2 and 10 are able to purchase, are able to be purchased. So basically 2 3 4 5 6 and up to 10. So the answer is 10 minus 2 plus 1. This is 9. So therefore 9 is the answer. Okay. So that's the solution to this. And now I'll show the code. So int nk, c in nk, vector int a of n, c in a, and then I input the vector a, and I sort a dot begin, a dot end. Then I have a set of int s, or multi-set, like doesn't matter actually. So what I'm doing is, for int I equal to 0, I less than I plus plus, I'm checking for the condition that can I actually buy this house. So if absolute value of I minus n minus I minus 1 is less than equal to k plus 1, then s dot insert a of I. Okay, so I'm just inserting all of the houses that I can buy, and finally just print the maximum value minus the minimum value plus 1. Right, that's the answer to this. Okay, so even if we just took set here, not a multi-set, then also it is fine, because the maximum and minimum value will remain same. All right, so let's move on to the problem number C now. Like which was div 1a. Actually I was in the division 1, so my submissions are there. So I'll open from there. Okay. So the Div 1A or Div 2C was this sports betting. The boarding process for various flights can occur in different ways, either by bus or through by telescopic jet bridge. Every day, exactly one flight is made from St. Petersburg to Minsk, and Vadim decided to demonstrate the students that he always knows in advance how the boarding will take place. Vadim made a bet with N students, and with the IA student, he made that he made a bet on the day AI. Vadim wins the bet if he correctly predicts the boarding process on both day AI plus 1 and day AI plus 2. Although Vadim does not know in advance how the boarding will occur, he really wants to win the bet, at least with one student, and convince him of his predictive abilities. Check if there exists a strategy for Vadim that allows him to guarantee success. Okay, so basically, the problem says that there is a man named Vadim. Okay, and like they have written a story about airplane boarding or something. I'll rephrase that. I will use rain or not rain. Okay, so Vadim claims that he's an astrologer. He's an astrologer, and he can predict that on the ith day, or let's say on the kth day, on the kth day, on the kth day, will it rain or not? Will it rain? Okay, so Vadim can predict this apparently. Like he is claiming that he can predict this, that on the kth day, will it rain or not? All right, and basically he made a bet with n students. He made a bet with n students. Like he made a prediction with n students. Okay, so for the ith student, he made a bet on the AI plus 1 and AI plus 2 days. Like basically, he claimed that on AI plus 1 day something will happen, and on the AI plus 2th day something will happen. Like he either claimed that it will rain and it will rain, or he claimed that it will rain and it will not rain, and or he claimed that it will not rain and it will rain, or he claimed that it will not rain on both the days. So basically, he predicted some information about raining about these 2 days. Okay, about these 2 days, he predicted information like for the IS student. So basically, he made a bet with n students that on the AI plus 1 a day and on the AI plus 2 a day, this will happen. Like we are not given that what he has predicted. Okay, what he has predicted we are not given. We are just given the days. Like on what days is he making a bet? Like he has made a bet with four students on day one. That means with four students he has made a bet that on the day 2 it will happen something, and on day 3 it will happen something will happen. So let's say that to student 1, if he says that on day 2 it will rain and day 3 it will rain, so true and true. Then to student 2 he says that on the day 2 it will rain and day 3 it will not rain. Then to student 3, if he says that on day 2 it will not rain and day 4 it will rain, and to student 4 he says that on the day both days it will not rain. Like let's say he makes these four bets, right? We are given that he has made this. We are given that he has made four bets about these 2 days. Like he has made a bet with four people on day one. So he has made a bet on day one. That means he has predicted the information about day two and day three, right? So about day two and day three, he has predicted that what will happen. So let's say that to the first kid, he says that it will rain on both days, and the second kid he says that it will rain on the day two and but will not rain on day three, and so on. So that's what he has guessed about the first student with the four students. So obviously, whatever happens on these 2 days, whatever happen on these 2 days, he will win at least one bet. Like out of these four bets, he will win at least one bet, right? He can guarantee that he will win. He will win at least one bet, right? So since it is possible to do the betting like that, like since it is possible, to make these bets, like make these four bets like that in such a way so as to ensure that he can always win at least one bet in any case. So therefore the answer is yes. Like of course, let's say if we had bet like this, let's say we were greedy, that let's say we had bet true and true twice. Like let's say we do something like this. Let's say on the first and second kid we bet that it will rain on both days, and to the third and fourth kid we bet that it will not rain, it will rain, and it will rain, it will not rain. So this is foolishness, utter foolishness. Why? Because now if it doesn't rain on both the case on both the days, if it doesn't rain on both the days, then we'll lose, right? So this is not a suitable arrangement. Like what I showed you earlier, that all the four possibilities I should bet so that I can ensure that I win at least one of them. So therefore the answer is yes. That's what the problem is asking. That does there exist a sequence of bets? Like we have to construct a sequence of bets such that we can be sure that he is able to win. Okay. Like of course, if he does it like this, then he can't win. But if he does it like this, that let's say he bets false and false, like he has bet all the four different cases, then he can win. So then he can win. So since there exists, like since there exists a way to make these bets, to make these bets such that he will win at least one bet in any case. So since he is able to make these bets such that he'll win at least one bet in any case, that's why the answer is yes, right? But let's say to test case 2 there are 2, 2 and 2. So like we are making a bet with three students that what will happen on day 3 and day 4. Like we are making three bets on day 2. So that means that we are making some bets with day 3 and day 4. Like we are predicting that what will happen on day 3 and on day 4. So I'll denote them by the circles, and in between these lines are the bets. Okay. So this line means that there is one bet between day 3 and day 4. Okay. So let's say I bet that it will rain on the third day and also it will rain on the fourth day. Then I try to bet with this one that it will rain, not rain on the first day, but sorry, third day, but it will rain on second day. And also I bet that it will rain on the third day, but it will not rain on the fourth day. So let's say I make these three bets. So I hope you understand the diagram, like how I have drawn this. I hope you understand the diagram. So um, if we make these three bets, then of course if it doesn't rain on both days, then we'll lose. Then we'll lose, right? And I think it is pretty obvious that it is not at all possible to ensure that we win always. Like it is not at all possible to ensure that we will win. Like there are no combinations that we can do, because like we are placing only three bets, right? We are placing only three bets, so of course we cannot ensure that we cover all the cases, because there are four cases, right? So therefore the answer is no. Okay. Now you might be thinking, like some of you might think that if there is some day, if there is some day on which we are making at least four bets, if we are making at least four bets on some day, on that day we can just choose all the four combinations. Like we can just bet all the four combinations, and we'll get at least one of them right. So therefore the answer is yes. And otherwise you would think, like else you would think that the answer is no, right? That is incorrect. Like of course the answer is yes in this case, but it is not necessary that otherwise the answer is no. Like it might happen that there is no day on which we are betting more than 4 or equal to 4, but also in that case also the answer is yes. So the example is given in samples also, like the third sample. The third sample is this, that 24324, right? Or 22344. So we are betting, like what we are doing is we are betting twice on the day 3 and 4. Like on day 2, we are betting two with two students. So basically, we are betting about the day 3 and day 4. So day 3 and day 4, we are betting twice. Then one bet on day 3. So day 4 and day 5, we are betting once. And one bet on day 4. So day 5 and day 6, we are betting twice. Alright, correct? So now, actually, I can construct one thing so that it is always possible to win. Okay, so I'll construct that. So basically, what the idea here is, just fix this thing, like just bet false and false here. Okay, and a true here and a false here. Like just consider these two bets. Okay, so now if a false comes at the 4, like if on day 4 the rain doesn't happen, then we'll win. Like we'll win at least one of these things, because either it is true or true false, or it is false false. Like if the 4 is a false, then 3 can be either true or false. So we'll win either this one or this one, right? So if 4 is a false, then we are done. We are sorted, right? But what if it is a true? Like what if 4 is true? If 4 is true, then we need to ensure that we have a way to win. Like we win at least one bet. So how do we ensure that we win at least one bet? Like just put a true in here. Like just guess true here, and let's say we guess false here, right? So if there is false here, then we win. Like irrespective of whatever there is here, like whatever there is on these first two, we don't care. If there's a false here, then we will definitely win. Why? Because either there will be a true here or a false here. So if there's a true here, then we'll win this bet. Or if there's a false here, then we'll win these two bets, like one of these two bets. So therefore, if there's a false here, we will win either one of these three bets, right? But what if there's not a false here? What if there's a true here? Again, the same thing happens. That what if there's a true here? So in that case, we'll try to put false here. Like we'll try to guess true. We'll try to guess true here in these two bets. And since we have two of them, in one of them we'll bet true and another of them we'll bet false. So now whatever happens, I will definitely win. Like if there is false here, then we'll win either one of these three, right? That's what I showed you earlier. And if there is true here, then we'll win either one of these two, right? So that's what we can guarantee, that we'll always win a bet by betting like this. Okay, like these five bets, as you can see, this one bet, second bet, third bet, fourth bet, and fifth bet. We can assign these true and false in this way and ensure that we are always winning, right? So that's why the answer to this test case is yes. Okay, so I think the problem is clear now, and there is some intuition going on in your mind that you can try and uh, like elaborate. So now I'll go to the solution. All right. Now the first thing you will notice is that how I have made this representation. Like I have drawn this thing. Like this data that I have here, I have drawn this in a very good way. Like there are four ones. That means I am betting four times in between 2 and 3. So sorry, between 2 and 3, I am betting four times. So I'll draw that like this. That I have a 2, I have a 3, and in between I have four lines. So they are the four bets, right? Then let's say in test case we are betting on the second day thrice. I mean, so on second day we are betting thrice. That means we are betting about day 3 and day 4 three times. So on day 3 and day 4 we are betting three times. So that's what I'll draw it like that. And the test case 3 also you saw that I'll draw it like this. right? So in general, my input will look something like this. Like there will be some days, there will be some days, okay, on which I bet. Like let's say I bet this and this twice. Then let's say I bet on this and this. Let's say I don't bet on these. Like I never bet on this. Then let's say I bet on this and this three times. And let's say I bet on this, and then let's say I bet on this twice. So this is one possible input. Okay, and how can let's say I just number these. So 2, 3, 4, 5, 6, 7, 8. So this diagram will be made for the input which one, like two bets between 2 and 3. So one twice. Then we have 3 and 4. So two once. Then 4 and 5 ke beech mein there are no bets. So we don't make any bets on day 3, right? Then between 5 and 6 there are 3 bets. So we are making 4 3 times. Then 6 and 7 once. So 5 once. And then we have this 6 and 6. So I am saying that for this input, this is my diagram that I will make. This is my entire diagram, right? And obviously it is pretty obvious that since these two components are disconnected, they are disconnected, right? So therefore they don't influence each other. Like they don't depend on each other. Like whatever bets I make here, FT, TF, like whatever I make here, it doesn't affect the other one. Like they are completely independent. These two components. So actually we can just find their answer independently. We can just find their answer independently. And if any one of the answers is yes, like let's say the answer for this is no, and the answer for this is yes, like we can win at least one bet in either one of these, then we'll print yes for this entire test case. Like for this entire test case, we'll print yes, right? So that's what I'm doing. That I am handling different components one by one separately. Okay. Uh, yeah. So now how do I find the answer for the components? Like okay, how do I find the answer for a one component is connected, right? So how does a component look like? Let's say that a component looks like this. It is connected, right? So there are some edges, like there are some number of lines in between these. Like for example, um, let's say that here, okay, so since it is a component, therefore there must be an edge between every pair of adjacent vertices, right? So there must be an edge between these. Now the thing is that what is going to happen, we can see that what is going to happen is that there will be some number of times these edges will come. Like what I'm saying is that let's say here the edge comes three times, here the edge comes two times, here the edge comes one time, and two times and three times. So basically we'll get a sequence of numbers, right? Like for this thing we'll get 3 2 1 1 2 3, like three edges, two edges, one edge, two edges, and three edges. So that's what I am getting, right? Now my claim is that if there are at least two numbers, like in this list of numbers, if there are at least two positions such that that number is greater than equal to 2, like let's say that this array is b, okay, let's say that this is the b array. So if there are two indices I, if there are two i's such that a of I is greater than equal to 2, then the answer is yes. Not a of I, sorry, b of I mean. b of I is greater than or equal to 2, then the answer is yes. And also if a of I is greater than or equal to 4, like if any one of these numbers are at least 4, like let's say there are 4 edges here, then of course we can just bet all 4 of these here and we'll win. So therefore if a of I is greater than or equal to 4, then also the answer is yes. Okay, and otherwise the answer is no. Like what is the otherwise case? That let's say bi greater than 2, I mean, okay, here also I made a mistake, that bi greater than or equal to 4, right? So let's say that bi greater than or equal to 2, I call it special vertices or special indexes. Okay, so special means that um, it is at least 2. All right. So yeah, if there are at like only one special vertex or only one special index, like all of the other ones are 1, and I have a, a non one, like in between I have a non one, then the answer is no. Or if all of them are 1, if all of them are 1, then also the answer is no. Otherwise the answer is always yes. Okay, so how do I prove that? Like how do I verify that the answer is yes? If there are two indices such that there are at least 2 in them, then the answer is yes. So let's say that I have some component, I have something like this. Okay, and let's say this is the position where I have at least 2. See, if I can make the answer for 2, like if I can make the answer for 2, then of course I can make the answer for 3 as well. Like if it is yes for 2 here, then of course if I add another edge, then it is yes, because that is an extra benefit. So I'll just answer for this thing. For this case, I'll show you how to create the answer. Okay, so the idea is same, like okay, this is one index where there are 2, and this is one where there are 2, and you need to assign. So what you can do is the same thing that we did above. Like what we did here, we can do the same thing. What we can just do is um, assign true false here and false false here. So if there's a false here, then we are done. If there's a false here, then we are done. But what if there are true here? If there's a true here, then we are not done yet. So we'll guess true here and false here. So if there's a false here, if there's a false here, then we are done. But that is, what if that is not the case? So we'll guess true here. Like if there's a true here, then we'll not win any one of these things. Like if there's a true here, and let's say a false here, then we won't win any of these bets. So the problem only lies when there is a true on this bet. Okay, so to handle that, I'll bet a true here, and let's say I bet a false here. So if there's a false here, then also I will win. But if there's a true here, then I'll still getting a problem. So again I'll bet true here and false here. So if there's a false here, then I'll win. But if there are true here, then I'll lose. So I'll guess true and false. Sorry, true and false. Okay. So this is how you can actually make these bets. And why does this work? So again I'll explain this for your sake. That there are two cases, right? There are two cases that either there is a false here or a true here. Okay. So if there's a false here, then we are sorted, because either one of these will be the answer. So we are sorted. But what if there's a true here? What if there's true here? Then what we'll do? Then simply um, we'll guess true false on this edge. So if there's a false here, if there's a false here, then we are done, right? But what if there's a true here? Then again we'll guess true and false here. So if there's a false here, then we are done. But if there's a true here, then we are still going. So if there's a true here, so we'll guess true and false. So if there's a false here, and so on. So um, if there's a false here, then we can win this bet. But if there's a true here on this index, then we'll guess true, like That's why we'll guess true, true, and true, false. So if there's a true here, then we'll win this. If there's a false here, then we'll win this. And like, I think you get the point. So if you still don't get the point of this, like, so what I'm doing is I'm just numbering it for your sake. So let's number it 3, 4, 5, 6, 7, and 8. And if you still don't understand how uh, this arrangement works, okay, like if you still don't think that I'm not winning in all the cases, then just try to make a case. Okay, like just look at these bets, just look at these bets, all right, like all of these bets, just look at them and try to create an arrangement for which I'm not winning. Like these 6 days, 3, 4, 5, 6, 7, 8, these 6 days, for them try to create an arrangement for which I'm not winning. Okay, like for example, for 3 if we have false, for 4 if we have true, uh, for 5th if we have true, for 6th if we have false, for 7th if we have true, and for 8th if we have false. Then which bet will we win? We'll actually win this bet, that on fifth day it is true and on 6th day it is false. So we'll win this bet. And if you don't understand that how this configuration works, then I challenge you to try and create a case where I'll lose, like where all of these bets will not be satisfied. Okay, so I'll challenge you and try to think of it yourself, such a case, and then comment on the YouTube video. Like just try to think of the case, that on which case does this fail, and then comment on the YouTube video and I'll reply that you are wrong, and the case that you gave can be handled by this bet. Like this bet will be won in your case. Okay, so that is the best way. If you don't understand this, like if you still don't understand how this is working, just try to create a case, and you won't be able to do that, and then you'll realize that it is not possible. Okay, and this is working fine. All right, so yeah, if there are at least two occurrences of numbers which are greater than or equal to 2, then the answer is yes. Like even in this case, like let's say we have this case, something like this, like we have 3, 1, and 2. This is also true because there are two indices on which there are at least two bets. So of course 3 works because we were able to make bets only using these indices, like only using these two, this one and these two, we were able to win. So of course if you add one more bet, it is just beneficial for me only, right? But okay, so it is not possible if otherwise, like if at least there are two positions such that bi greater than or equal to 2, then the answer is yes. And if any bi is at least 4, then of course it is yes. Otherwise it is no. Like otherwise it is no. Like what I'm saying is that in my component, if there's only one occurrence of my at greater than or equal to 1, like let's say this is what I have. So in this case, the array that I have is 1 1 3 1 1, right? So there's only one occurrence of a number which is greater than or equal to 3, greater than or equal to 2, I mean. So since it is the only one, so the answer is no. And why the answer is no, I'll try to like give an intuition. I don't have a proof of this, but I'll try to give an intuition. Okay. So the thing is that let's say you make three bets right here: true, false, 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 and true, true. Let's say. So here, false, true is not there. Like, what if this is false and this is true? So you'll try to handle this using this edge. You try to handle this false using this edge, but let's say you try to guess here true, but what if there is false here also? So again you'll try to guess false and then true, but what if there's a false here, right? And this side, if there's a if there is, like, what case have is left, this false and true is left, right? So you will try to guess true here, but and then let's say you guess true here, but what if there's false here? So you'll try to guess false here and true here, but what is there false here? So basically this chain reaction will keep going on. It will not end unless you have another index at which there are two edges, at least two edges. and at that point only it will terminate. Okay, so if you have only one location where there are at least two edges, then the answer is no. Like, as you can see for this configuration, for these bits, uh, we are not winning if we are not winning if the range is like this. Like, if it is false, 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 true, false, false, then our bets don't work. And like, it is not possible at all to assign these bets also. So that's why the answer is no if this is it, this is the test case, like 1 1 3 1 1, or basically 1 2 3 3 3 4 5. So this is the test case is this one, right? So for this test case, the diagram will look like this, and the answer will look like no. Okay. So I'll show more samples. Like, I'll show this sample as well. We have 1 1 1 2 3 5 6 6. The sample is this: 1 1 1 2 3 5 6 6. So okay, first of all, as you can clearly see that these values and these values are independent, because there's a 4 missing right here. There's a 4 missing here, so there will be one gap in between. So therefore, these two components are independent. So we'll solve them separately. So if I make diagram of this component, so it will look like what? There are three ones, then there are two. There is a single two, single three. This is one component, and if I make a diagram for this one also, then it will look like a single and then a double, right? So as you can see that for these both components, um, the answer is no. So therefore, the final answer is also no. Like, we need at least one yes in our answer to ensure that we win at least once. So therefore, the answer to this is no. Okay. So yeah, this was the logic for this problem, and now I'll show the code for this. The implementation is nice. Like, implementation is like, I'm using a vector and so on. Like, what I'm just doing is, this is my input array, right? Like, this is my A. This is my A array. So I am creating a new vector called V, and I am pushing back the numbers into that vector V until I encounter a missing number. Like, I just push back all of these numbers into this vector V, and then I saw that this 5 has directly come. Like, the difference between this 3 and 5 is more than 1. So at that point, what I'll do is that I'll check this V. I'll check this V, that does it have the answer as yes. And if it has the answer yes, I'll print the answer. And otherwise, I will just delete all these elements. Like, I'll delete all the elements from this V, and again I'll start from this 5. I'll put this 5 again, and then I'll again wapis, and then I'll again put this 6 and 6. So my vector V would become 5 6 and 6 in the end, and then again I'll check for 5 6 and 6. So that's how I am breaking into components, right? So I'm doing LLN CNN IAAN and sort a comma I plus n. So input the array and sort it, and then I have a vector V. So for int I equal to 0, I less than I plus plus, if it is the first element, or ai minus a of I minus 1 is less than equal to 1. Okay, that means that there is no gap between this one and the previous one, or the gap is at most 1. So it is kind of continuous. It is the same component. So I'll push back a of I, and of course it is the first element, then I'll push back a of I. And otherwise I'll have to perform, like, I'll have to check for this vector V. Like, currently whatever we have in the vector V, I'll have to check that is the answer valid, like, is the answer for that yes or not. And to check the answer for that, I'll make the frequency array. Like, for example, if I have V as 1 1 1 2 3 4 4, okay, then I will make a new vector U, which will be 3 1 1 and 2. Like, basically the three numbers are there together, then there is a single number, then single number, and there are two numbers together. So 3 1 1 and 2. So now if there are more than two indices more than two indices such that the number is at least 2, then I'll print yes. And if there's an index such that number is at least 4, then also I'll print yes. Otherwise I'll continue. Like, of course I won't print no, because I'll have to check other components as well. So yeah, that's what I'm doing here. I'll make a new vector u, and if v of j equal to v of j minus 1, then I'll just increment the last element, and otherwise I'll create a new element, and one I'll push back 1. Okay. So if the max element of u is at least 4, then I'll print yes. Okay, and return. And otherwise I'll count the number of elements. I'll count the number of elements such that u of I is greater than 1. So count plus plus. So if count is greater than or equal to 2, then I'll print yes and I'll return. Right. So this is the code for checking. This is the code for checking this v. Right. And finally, I'll just insert the a of I also. Like remember that I also have to insert a of I. Like what I did was I inserted these 5 elements into this v. Then when I came at this 5, I saw that there's a gap here. So I just processed this vector v. But now also remember that we have to insert this 5 as well. So I insert this 5, like I just assign v dot assign 1 comma a of I, which means that one element, that is a of I. The v will contain one element which will be a of I. Alright. And yeah, in the end also, like when the for loop ends, then at that point whatever the vector v is, we also will check that. We'll check that vector also. So I have just copied the code from the above only. Like um, as you can see that this code and this code is the exact same. So I'm just checking the vector v, the final vector v, and I'm printing yes if it is yes. And finally, if I am not printed yes and I have not returned, then the answer is no. Okay. So that is the solution to this problem. All right. So yeah, if you have any doubts, then you can ask in the comment section, and I'll move on to the next. So div 1b we have, and which is div 2d, baggage claim. Every airport has a baggage claim area, and Balvesovo Airport is no exception. At some point, one of the administrators at Sheremetyevo came up with an unusual idea to change the traditional shape of the baggage claim conveyor from a carousel to a more complex form. Suppose that the baggage claim area is represented as a rectangular grid of size n by m. The administration proposed that the path of the conveyor should pass through cells P1, P2 up to P of 2k plus 1, where Pi is xi yi. Okay. For each cell Pi and next cell P of I plus 1, these cells must share a common side. Additionally, the path must be simple, meaning that no pair of indices I not equal to j should the cells Pi and Pj coincide. So all of these 2k plus 1 cells should be distinct. Unfortunately, the route plan was accidentally spoiled by spilled coffee, and the only cells with odd integers of the path were preserved. That is, P1, P3, P5 to P of 2k plus 1 was preserved. Your task is to determine the number of ways to restore the original complete path given these k plus 1 cells, and print it modulo 10 to the power 9 plus 7. Okay. So, like, the thing is that we have been given a grid. Okay. Like, there is a grid, alright, and on that, what we know is that there are some cells. Okay. There are some cells, like, let's just take a test case. Okay. So let's say grid is of 2 by 4 size. 2 by 4 size grid is there. So I'll make that grid. 2 rows and 4 columns. 1, 2, 3 and 4. So 1, 1. So the first point is here. Then 2, 2. So the third point is there. And 2, 4. So the fifth point is here. So we need to fill in the second and fourth points. Like, we need to complete the path. Right. So actually, the thing is that either it can be this 1, 2, 3, 4 and 5, or it can be like this, that 1, 2, 3, 4 and 5, right? These are the only two options, because all the adjacent elements must share a side. Like, if I have 2 after this 1, So these 1 and 2 are adjacent in the grid, they are sharing a side. That is one rule. And also another rule is that the path must not overlap. Like I can't do something like this is 5, then we go to 6, then we go to 7, and then again we go to 8. So this 8 cannot be here because there's 4 here already, right? So yeah, that is the thing that we are trying to do. 1, 3 and 5. So either it can be 1, 2, 4, 1, 3, 1, 2, 3, 4 and 5, or it can be like this 1, 2, 3, 4 and 5. So therefore the answer to this is 2, right? Then second test case we have like 1, 4, 1 and 1, 1, 1, 4. So like 1 by 4 grid we have. The grid is of size 1 cross 4. 1, 2, 3, 4. So I have 1, 1 and 1, 4. So the first cell is this, third cell is this, and I have to place a 2 here such that they are adjacent. But of course there is no way to do that, right? I cannot place 2 anywhere. So therefore the answer to this is 0. Correct? So now we simply need to count the number of ways to put this, right? So what can I do? What can I actually do to solve this? So the first of all, of course, the condition is that any two adjacent cells. Just 1 minute. Yeah. So any two adjacent cells, like I mean not adjacent, like in the input what they have given, like they have given the alternate cells, right? Like they have given P1, P3, P5, P7, and so on. So let's say uh, from P1 and P3, what I'm saying is that the distance between them should be exactly 2. Like between P1 and P3, the distance should be exactly 2, right? Because when we are moving to P2, like when we are moving from P1 to P2, the distance from them is 1. Like let's say P1 is right here, then we have P2, and then we have P3. So as you can see, the distance is 2 between them, right? So that is the sufficient condition. I mean that is necessary condition that there must be a difference of 2, like a distance of 2 between any two adjacent vertices. So as you can see that in this input, like 1, 1, 2, 2 and 2, 4. So between 1, 1 and 2, 2, the distance is 2, and between 2, 2 and 2, 4 also, the distance is 2. So therefore the answer is not 0 in this case. Then in this case, the distance between 1, 1 and 1, 4, it is 3 actually. So therefore the answer is 0. So I just did that if the distance is not equal to 2, right? Then I'll just directly print 0. Correct. That is one thing. Now, now what to do? Like now, how to count this? So the thing is that we have like this is P1, this is P3, right? So P2 can actually come in two types. Like either P2 can come here or P2 can come here, right? Either P2 can come here or it can come here. So what that means is that we can choose between these two cells. Okay. So that is happening because they are diagonal. Like since they are diagonal elements, therefore we have to choose. Like we can either choose P2 here or P2 here. But let's say P1 was somewhere here and P3 was at distance of 2 but not diagonally. Like maybe it was something like this. Then that would mean that P2 has to be here, right? P2 has to be here. Okay. So that's one constraint that we gotta think about. That uh, if they are vertical or if they're horizontal, like let's say even P3 is here, let's say P1 is here, P3 is here, then P2 has to be here between those. So only in the case where they are diagonal, only in the case where they are diagonal, we have two options. Like either P2 can be here or P2 can be here in one of these cells. right? So now how do we count this? Like how do we count the number of uh, arrangements? See, what you can think is that, okay, let's say we are given k plus 1 points, right? Like we are given, let's say for example, p1, p3, p5, p7 and p9, let's say. Okay, so let's just say that this board is a little bit bigger. Let's make a big board. Okay, and we have been given these cells, right? So let's say p1 is here, p2 is here, then let's say p3 is here, then p4 is here, and p5 is here. So from p1 to p2 you have two options, either this one or this one. Then from p2 to p3 you have two options, either this one or this one. Then from p3 to p4 you have two options, this one or this one. And from p4 to p5 you have two options, this one or this one. And as you can see that these all of these options are independent. Like whatever I choose in this option, I still have these two options right here, right? So therefore the answer in this test case is just 2 to the power 4, which is 16, right? So the answer is 2 to the power 4. But this will not work every time. Like this technique will not work every time, because let's say for example I have p1 here, p3 here, and p5 here, right? So now um, between p1 and p, so p2 can be either here or here, p2 can be either here or here, and p4, like p3 and p5, so p3 goes to p5, so p4 can be either here or here, right? So basically if I choose p2 to be here, then of course I cannot keep p4 here, because only one uh, thing can be there in one cell. So if p2 is here, then p4 cannot be here, and if p4 is here, then p2 cannot be here. So only one of them can be here. So actually, instead of 4, like we would guess that 2 to the power 2 is the answer, which is 4. But actually, the answer is 3 in this case. The answer is 3 because, um, like, either we can have both p2 and p4 in the bottom cell, like this can be the case, p1, p2, p3, p4, p3, p4, or one of them can be in the above cell. So let's say p2 can be here, right? Or p4 can be here. So p2 is in the bottom cell and p4 is here. So these are the three cases that are there. So our idea of 2 to the power 2 doesn't actually work, because there are some interrelation also between the cells. Like the cells may not be independent, right? There is some interrelation between those cells. So how do we actually deal with that? Now actually one more complexity is there. Like in this problem, there is one more complexity. And what is that? I'll show you. Okay. So let's say I have a P1 here, then a P2 here. Sorry, not P2, I mean 3, and P5 here. So from this P3 to P5, this P4 is right here, correct? So P2, like initially we would think that P2 has two options, like this one or this one. P2 has two options, either this one or this one. But then we would say that then we would see that this P3 and P5 are horizontal. So therefore P4 has to be here, P4 has to be here. So therefore the answer, like actually P2 has to be here. Like P2 doesn't actually have two options. P2 has only one option. It has to be there, right? So that's why this is one more complexity of this problem. Okay, so this is why the problem is actually very complex. And the idea actually for this problem came to me by another problem. Like if you just solve this problem, just wait. Desk disorder code forces. So if you just search for this problem, I had actually done this problem recently. Like today is 27th April. I had done this on 6th April. Like 3 weeks ago, I had done this. And basically, this problem has the same idea as this one. like if you just read this problem once, then you will see that this has the same idea as this one. Okay, and so that's why I could solve this problem in contest, right? But to think of this idea, like to solve this problem, it took me one whole day. Like I was thinking for one whole day, and after that only I got the idea of this problem. Okay, so um, so like please don't ask me that how do you get the idea for this problem. I don't know. Like what is the intuition? I don't know. I can only tell you solution to this problem. Like maybe if you had done this beforehand, then you would be able to do this also. Okay, but just don't ask me that what is the intuition, because even I don't know that. Just that I had seen the idea previously, so I could apply this here. Okay, so the idea actually is that you can make a graph. Like okay, some people might say that graph कहाँ से आ गया. Even I can't tell you graph कहाँ से आ गया, but I can tell you that graph से कैसे होगा. Okay, so um so yeah, what we'll do is for every event index we have, right, like we are given p1 p3 p5. Let's say we have another p7, p9, then we have a p11, we have a p13. So let's say we are given these points. Okay, this is nice up arrow like this. But yeah, we are given 13, we are given these till p13, and we are supposed to fill in like p2, p4, p6, p8, p10, and p12. Okay, so we are supposed to fill in these vertices such that you get the like the condition, right, that p2 must be either here or here, then p4 must be here, then p6 must be either here or here, then p8 must be either here or here, right, and p10 must be here, and p12 must be either here or here, right. So that is our conditions. So what graph I am telling you to make is, make a graph where it has six edges. Like you want to well, like assign six numbers, right? You need to assign six positions. So make a graph which has six edges. Okay, so there will be one edge for each position, like for each um, all of these p1 p2 p4 p6 p8 p10 p12, like where to put p2, where to put p4, and up to where to put p12. There will be an edge for that, okay, in our graph. And let me just label these vertices. Like let's say that this is a, this is b, this is c, this is d, this is e, this is f, this is g, this is h. Okay, so and this is I. Okay, so I have labeled these cells. All right. So in my graph, there will be six edges, one for each index of p. Okay, and there will be these vertices. Like the vertices will be these cells, like A, B, C, D, E, F, G, H, I. These cells will be there, and I will add an edge between two cells if that P2, like let's say my P2 can be where? My P2 can be either in A or C. Like this P1 is here, P3 is here, right? So my P2 can be either in A or C. So what I can do is, what I will do is, I will like in between my A to C, like between my A and C, I will add an edge. Okay, which is of P2. Like this edge is of P2. Like not weight. Like this edge doesn't have any weight. Just that this edge belongs to P2. Like because of P2, I have made this edge, right? Then for P4, what are the two options? P4 actually has to be on C, right? P4 has to be between this P3 and P5. So P4 has to be on C. So I'll make an edge from C to C. Okay, like see, for every number, we have two options, right? Like either we have one option or two options. Like for example, for P2, we had two options, A and C. So we made an edge between A and C. And but for this P4, we have only one option, which is C. So we make an edge from C to C. Okay, that basically. So yeah, we make an edge from C to C, and the edge is not directed. Like okay, so the edge is from C to C, which is P4. Then what we'll have is for P6. for P6, what are the options? Like P5 and P7. So between E and F, so either E or F. This is my P6. Then um, this P8. P8 will be between P7 P9. So either I or F. So I or F. So this is P8. And then I have P10. So P10 is on G. So obviously I'll make a loop from G to G. And P12 is either D or H. Okay, it is either D or H. So I'll make an edge between the nodes D and H, which is P12. This is P10, right? So now that I have made this graph, so like now I have this graph. So now I will tell you what is the purpose of making this graph. Like, why did I make this graph? What is the benefit? Now, actually, what you can say is that for every P2, P4, P6, P8, P10, P12, you actually have to assign them one cell, right? Like, let's say this P2 is there, like this edge is P2. So either you have to assign this P2 A or C, right? Like on the grid, you can see that either P2 can go to C or it can go to A. So basically, this edge, this edge, you either have to give to A or to C. Okay. Then for this P4 also, this P4 edge, you either have to give to C or to C. So like, of course, you have to give to C. Then for this P6 edge, you either have to give it to E or to F. And like so on. That is how it will work. So now it boils down to, like, you want to give all the edges a direction basically. Like, let's say I give this P2 this direction, and I give this P4 this direction. I give this P6 this direction, P8 this direction. So what does direction mean? Direction means that, like, if this edge is pointed towards A, then that means that I am giving P2 to A. Like, I am placing P2 at A. Okay. So we want to give the direction in such a way that my every node in degree, like, there is no node on which the in degree is at least is 2. Like, what I'm saying is that we cannot do something like this. Like, we cannot do that we give P6 to F and P8 also to F, because in this case the in degree of F becomes 2, which is not allowed, because we cannot put two different things on the same F. We have to choose one. So the problem now boils down to give these edges a direction, so that the in degree of every node is either 1 or 0, right? So this problem, how to solve that, that's what I learned from this problem. In fact, using this idea, like making this graph also, I learned in this problem. Like in this problem, I made this graph, okay, and I learned that idea and applied that right here. So I just made this graph, and now I have to count that how many possibilities are there. Like, in how many number of ways can I do that? Okay. So let's just count it manually for this test case. Like, let's say I don't, I haven't assigned the directions right now. So let's say I erase this. Now see, of course, the different components, they're independent of each other, right? Like, whatever I choose here doesn't depend on what I choose. Like, doesn't affect what I choose here. So different components are independent of each other. So what I choose here doesn't affect what I choose here, and doesn't affect what I choose here. So actually I can just find out the number of ways for each of them. Like, suppose W1 number of ways for this component, then W2 for this component, W3 for this component, and W4 for this component. Number of ways. So my final answer would be just the product of all of them. W1, W2, W3, W4. Right. So the thing is that, okay, now how do I find the answer for one component? All right. So let's find the answer for this thing. Now, of course, this P4 edge has to be on C. It is a self loop. So I'll make it to C. right? And so of course then P2 has only one option left, that it has go to A. So there's only one way to do this. There's only one way to assign the directions, right? Then let's come to this one. Now in this case, there are three options. Okay, there are three options, namely what? Like we can actually directly like this, like give P6 to F and P8 to I, or we can give P6 to E or P8 to F like this, or we can give P6 to E and P8 to I. All right. So that's what we can do. So there are total three ways. Total three ways there are, and let's say in this case I have P12. I have to attach it to either D or to H. So there are two ways, of course. So either to D or to H, and this G thing, like this P10, I have to attach to G. So there's only one way. All right. So my W1 is 1, W2 is 3, W3 is 2, and W4 is 1. So basically, the total number of ways is 6. Okay. So to fill this grid, there are in total 6 possible ways, and you can actually fill P6, P8, and P12 independently. And there's only one way to fill P2, P4, and P10. Okay. So, anyways, there are total 6 ways. But now the question arises is that यहाँ तो manually कर लिया मैंने, like I did the manual calculations right here by just counting it like this. But how do I actually calculate it? Like for a given graph, how do I calculate the number of ways to assign the edges, right? So to do that, what I can do is just make some cases. So of course, in a graph, if there are different components which are disconnected, then we'll of course find the answer for each connected component one by one and multiply them. That's what I told you, right? So now we just gotta learn that how do we, like given a connected component, like given a connected component of a graph, so how do we figure out the answer to that, like the number of ways to assign the edges so that every node has in degree of at most one, right? So let's do some casework now. Okay, so we want to find out that a connected component given a connected component, how do we figure out that how many ways are there, right? So actually there are three cases. Okay, so let's say that our component has v vertices. In our graph, the component has v vertices. Okay, so therefore, since it is connected, right? So therefore edges have to be at least v minus 1. Like edges have to be at least v minus 1, right? This is one fact of a graph, right? That if a connected graph is there having v vertices, then at least v minus 1 edges you need, right? At least v minus 1 edges you need. So like for example, if you have these three vertices, to connect all of these three vertices, sorry, four vertices, you need at least three edges. So that's why that's what I'm doing. That's what I'm saying, that the number of edges is at least v minus 1. Okay, so now in my component, either the edge, like I'll make three cases. Okay, so let's say I have v vertices. If let's say I have v vertices, so either the number of edges can be equal to number of vertices minus 1, or the number of edges can be equal to the number of vertices, or it can be that the number of edges is greater than the number of vertices, right? That is the thing. Like there are three cases, this one, and this one. Okay, so now let's start with the bottom. If number of edges is greater than number of vertices. Okay, so my claim is that in this case the answer is 0. Why? Because see, what eventually what you have to do is that in your given graph, you actually have to assign each edge a node, right? You need to assign each edge a node such that every edge, like such that every node has in degree of either 0 or 1. So basically, you need to assign each edge a node such that no node is assigned at like more than once. But let's say in this graph there are 5 edges, but there are only 4 nodes. There are only 4 nodes, right? So of course you cannot assign them because there are multiple nodes, like there are less number of nodes and there are more number of edges. So of course you cannot assign 5 edges to 5 unique nodes, because there are only 4 nodes. So when you assign, there there will definitely be repetition. So definitely, if E is greater than V, then the answer is equal to 0. Like if in my connected component, if E is greater than V, then the answer is 0. Then let's say my E is equal to V, that case. Okay. So what does that mean? E equals to E equals to V. Like if we have a connected graph, if we have a connected graph and our number of edges is equal to the number of vertices, then that means that there is at exactly one cycle. Like in my graph, there is exactly one cycle. Okay, that is the thing, that if I have V edges and V vertices, that means that I will have exactly one cycle in my graph. Okay, right? So or maybe there's a self loop, like either a cycle or there can be self loop. Like let's say that something like this. So this edge, this edge, and this edge, there are 3 edges. So in this graph also there are v is equal to E, and in this one also v is equal to E. But it is obvious that there is only one cycle in such a graph if v is equal to E and is connected. Like my claim is that if a graph is connected and the number of vertices is equal to number of edges, then there is exactly one cycle, and I am counting this self loop also as a cycle. Okay, so in this case, if we have a cycle, then how many ways are there? How many ways are there? Let's count that, right? So how do we count that? Like, okay, let's consider this edge. Just consider this edge. Okay, so let's say if we give direction this, if we give it this direction, then of course for this edge I'll have to give it this direction, and then of course for this edge I'll have to give it this direction, right? So basically in the cycle all the nodes have been used. Like this node has been assigned, this has been assigned, and this has been assigned. Now the only option is that this node is there, so it has to be assigned. So we have to assign it like this, right? So the cycle can be clockwise, or actually it can be anti-clockwise as well. Anti-clockwise as well. Like we can assign it like this, ulta. Like we can do it so that this edge is assigned to this vertex, then this edge is assigned to this vertex, and this edge assigned to this vertex. So in this way also all of these 3 vertices are used up, and again I'll have to assign this edge to this vertex, right? So there are 2 ways, okay, that the cycle is either clockwise or anti-clockwise, either anti-clockwise or clockwise. So there are 2 ways to do this. But actually in self loop case, it is only one case. Like since cycle is just of one length, so the anti-clockwise or clockwise doesn't matter, that they are same thing. So if it is a self loop, then the answer is only one, and if it has a cycle of length at least 2, then the answer is 2. There are 2 number of ways to do that, right? So if E is equal to V, then my answer is 2 or 1, depending on whether that cycle is self loop or not. Okay, so if E is equal to V, then 2 or 1. 2 or 1 if it is self loop, and 2 if it is not self loop. Not self loop, right? And now we have the case that number of edges is equal to number of vertices minus 1. That means that the component is a tree, right? The component is a tree. So like for example, it could be something like this, right? This is a thing, and we have to assign all of these edges to a name, to a vertex. Okay, so now as you can see that the number of edges is equal to 1 less than the number of vertices. So therefore after we assign all the vertices, there will be one vertex. There's always one vertex which will not be assigned, right? So let's think that what is that vertex? Like, let's assume that this vertex is that vertex. Okay, this is the vertex which is not assigned. So that means that all of these three edges have to be directed away from this vertex, right? So these vertices have been assigned now, and that means that these vertices, like this edge has to be assigned to this edge has to be assigned to like these two, like this, and since this has been assigned, so this edge has to be assigned like this, right? So as soon as we fix a vertex, that we should not assign this one, then all the other edges have been assigned automatically. Like, if we fix that, we want that this vertex should not be assigned, then all the other edges are fixed now, right? All the edges are fixed now. So like whatever vertex we choose, our arrangement is fixed, and there will be an arrangement. So for every vertex that we can choose, there is one possible arrangement. So therefore the total number of arrangements is just number of vertices, just the number of vertices, that is. So the answer to this test case is the number of vertices, right? So if it is a tree, then the number of ways is the number of vertices. If it is a cycle, like if it has one cycle, just one cycle, then it is either 2 or 1, depending upon if it's self loop or not. And if it has two cycles, let's say, then the answer is 0. Like, okay, what I forgot to tell you, that if E greater than V, if number of edges is greater than number of vertices, then that means that the graph has at least two cycles, right? See, what is the case, that if um, if there are three cases, right? If E is equal to V minus 1, then it is a tree. Then it is a tree. Then if E is equal to V, then it is like it has only one cycle. Okay, and if E is greater than V, then it has multiple cycles, right? So if it has multiple cycles, we don't want that. So in that case, the answer is 0. So yeah, this is the answer, and how you calculate that. Like for a given graph, you just find its components, and for each component you just apply this, that if it is a tree, then the number of vertices is V, number of ways is V, and if it is a cycle, like only one cycle, then the answer is 2, and if there are multiple cycles, then the answer is 0. So let's try to apply this on our this test case. Like, so we had here this component, we have in this component we have two vertices and two edges, right? So E is equal to V, second case, and also a self loop is there. So so my point is that the answer is 1, right? The answer is 1. Then in this component there are three nodes and two edges, so it is a tree. So the number of ways is 3. The number of ways is just the number of vertices, so 3, it checks out. Then again we have a tree with two nodes and one edge, so the number of ways is 2. And this component we have a cycle with a self loop, so therefore the answer is 1. So it checks out, like my logic is working, right? Now the only thing that is remaining is the implementation. So in the implementation, what you can do is just make a DSU. Okay, like just make a graph of all cells. Like, just make a graph which contains all the nm cells. Like, this has n rows and m columns, right? So there are n into m cells. So just make a DSU of size nm, okay? And whenever you see that there is an edge, like let's say for p2, what you will do is you will take the union of this a and c, like whatever is the index of this edge and index of this vertex of or this cell and this cell, you will take the union of them, you will join them in the DSU. And for every cell you will do that, like for p4, p6, p8, p10, p12, you will do that. And also you will keep track of the number of cycles in that DSU. Like, you will keep track if that DSU is a tree, if that DSU has one cycle, or if that DSU has multiple cycles. You will keep track of that. Like, you will just keep another vector in the DSU where you can store if that DSU, like that component, is a tree, or if it has one cycle, or if it has multiple cycles. So you can keep track of that. And how do you actually keep track of that? You can do it like, what you can just do is that when you are joining now, like let's say you have two components, let's say you have this one component and you have this one component, and when you are joining them, so if both of them don't have a cycle in them and you are joining different components, then of course the final component won't have a cycle in it, right? But then let's say you are joining two vertices in the same component, like let's say this is one component, one DSU, and you are trying to join these two vertices. Okay, then now you have a cycle, now you have a cycle, right? Okay, and like initially if you didn't have a cycle, like initially if it was a tree and you try to join these two, then you have one cycle, so you have transitioned from this tree to one cycle. Okay, but let's say you had one cycle already, and you try to join one more vertex, like let's say you join one this and this, you try to join this and this, then multiple cycles, like you have gone from this state to this state, like this component has now multiple cycles, so you will change that. Okay, and now, and what if let's say you have one component which has one cycle and one component which has one cycle, and you join them. So in that case, this final component will have multiple cycles, right? So that's what you can update. And let's say you have one component which is a tree, and one component has having multiple cycles, like something like this. Multiple cycles is there. So when you join them, this component will have multiple cycles, right? So this casework you can do in the DSU itself. In the DSU code, you will do this casework, and finally, you will just iterate over all the components, iterate over all the components, and find out that what type they are, and accordingly just multiply their answer, right? Just multiply by 2 or 1 or v or 0. Okay, and finally just find the answer. So that's the logic of this problem, and I'll just show you the code now. I'll just show you the code now. Okay, like this is my DSU code. I have these four vectors: vector of LL parent and SI, which is the parent and size vector in DSU, the normal vector, and I also have a vector of bool, psych1 and psych2. So psych1 is basically uh, psych1 is false, means there is no cycle. Then psych1 is true and psych2 is false, means that there is only one cycle. And if they are both true, then it means that there are multiple cycles. Okay, so psych1 is essentially true if there is at least one cycle, and psych2 is true if there are at least two cycles in the component. Okay, so this is find function and this is join function. So the main thing in join function, a is equal to find of a, b is equal to find of b. Now if a is equal to b, so we are trying to join a and b, right? So if there is a cycle in a already, then my cycle 2 of a is true, right? And also my psych1 of a is true irrespective of that. Like initially if it wasn't true, then I'll make it true, because now I have tried to join two vertices in the same component. Okay, so if a is equal to b, this is the case, and otherwise, again the small to large thing, if size of a is less than size of b, then I'll swap as a and b. Then I'll do parent of b equals to a and size of a plus equals size of b. Now I just need to update the cycle 1 of a and cycle 2 of a. So does a have a cycle and does a have two cycles at least? So a will have at least one cycle if either a the in initially a had a cycle, or B had a cycle. Okay, and A will have two cycles if either A had two cycles initially, or B had two cycles initially, or both of them had one cycle initially. So when you join them, they will have at least two cycles. So I'll update cycle 1 of A and cycle 2 of A like that. Okay, and finally in the solve function I have that basically I'll just glance through the code. I won't explain all of it, but yeah, this is my nm scene nm. I'm the DSU initialized here. I am initializing all cycles to false. Like all the components, they don't have a cycle. They are a tree. They are a tree with e is equal to 0 and v is equal to 1. Like they are the tree with one vertex and 0 edges. Okay, and then I have um, this useless vector, like which I did not use eventually. Yeah. So what I'm doing is um, yeah, first of all, for int I equal to 0, I less than k I plus plus, if distance of vi and vi plus 1 is not 2, then I simply return 0. I simply print 0 and return. Right, that is the case handling here. Then what I am doing is I'm iterating over all the pairs, and so the current one is A and the next one is B. So this C and D are the positions that where can this go. Like let's say that um, I have my, like let's say I have my 1 here and 3 here. So this cell is my A and this cell is my B. So I am seeing that where can this 2 go. So 2 can go in C or D, right? So if it is diagonal, like if A and B are diagonal, then C can be this and D can be this. And if A and B are uh, not diagonal, then C and D will be same. Okay, so C is equal to, okay, so if they are diagonal, this is the case if they are diagonal. So C is A dot first comma B dot second, and D is B dot first comma A dot second. And um, otherwise, C and D are just midpoint of both of them. So C is A dot first plus B dot first by 2, and A dot second plus B dot second by 2. And D is also same, right? And now I'll just join C and D. Like in my DSU, I'll join the components C and D, because that's what I'm doing, right? I'll join these two because the two can come either here or here. So I'm joining these two cells and I'm making the graph, right? And also I'm counting the number of self loops. Okay, I'm counting the number of self loops. ठीक है ना? Because finally what I'm doing is, if my component has a cycle, then I'll multiply it by 2. Like um, see, ideally what I should do, like what I'm doing here is um, f of I comma n into m. So I'm iterating over all the components. If parent of I is not equal to I, then that means that is not a component. Okay, so continue. Now if cycle 2 of I, then of course it has, if it has two cycles, then I'll print 0 and I'll return. Else if it has one cycle, then the answer, like then I multiply the answer by 2, right? Because that will contribute 2. But actually it can contribute 1 as well. 1 as well. Why? Because if it has self loop, then it will contribute 1. So to counteract that, I will divide by 2 to the power number of self loops. Like I have printed answer divided by 2 to the power number of self loops. So all the extra 2's that I multiplied here, they will be counteracted by this thing, right? And yeah, if there is no cycle, like okay, if there are two cycles, then I'll print 0. If there is one cycle, then I will multiply it by 2. And if there are no cycles, then I'll multiply it by the size of the component, the number of vertices in that component. And then finally, I'll just print the answer. Answer divided by the 2 to the power number of self loops. Because I overcounted those 2's. So I have to counteract them. So this is the model inverse of 2. Okay. So yeah, this was the problem. And actually this is a very nice problem. Like this one is rated 2100. So I think this one must be like around 2200 or 2300 at least. So if I check that, baggage claim is 2200. Yeah, on serious it is 2200, and like probably it is even more on code forces. Like I think it should be around 2300 if it is, like I felt it like it is around 2300. But yeah, anyways, so this was the solution to this problem, and I hope you understood. And like if you didn't understand, then I recommend you to solve this problem first. Like I recommend you that if you're trying a problem of 2300 or 2200, then you should think about it by yourself, and like that is the only way you will understand. Okay, and if you still have a doubt, then you can ask me in the comments. All right, so yeah, that was it for the today's PCD. And all right, so I'll see you all later, and bye bye.